see. Oh. So the video is not working on the slides. Normally you would see the cars moving around here on the front screen. So I'm Chris Benson. I am going to talk to you a little bit about deep learning and digital transformation. There's the video. It took a moment there. So almost didn't make it today. I'm from Atlanta, and we had a close call with a hurricane, and I had a broken foot. So forgive me as I hobble around the stage here talking. I have a cast boot on. This is me. I just left Honeywell, where I was the chief scientist for AI and ML for one of their global divisions. I built the capability there. And before that, I was at Accenture. And then I have some other activities around the AI world, such as a podcast and deep learning group. And so I do a lot of talking about these topics with different groups. I had my first start quite a ways back on this. For those of you who are old enough to remember, it's the original IBM PC when it came out. Did my first Hello World on that, and been doing data science and computer science ever since. So I got introduced to artificial intelligence before most people out there. It's been 26 years, and people are like, really? That far back? And that's because there was this plane that was built in the Atlanta area. And some of you may recognize it. It's the F-22 stealth fighter. It was built in the Lockheed, Georgia plant just outside of Atlanta. And they had a serious situation when it was still a prototype. There was a test going on at Edwards Air Force Base in California, and the plane was supposed to prevent the pilot from being able to crash it. So they were testing the avionics, and things did not go quite as they planned. The good news is the pilot was fine, and after skidding fire down the runway, he got out. But this somehow led to me getting into AI, and that was because this particular man was responsible as the engineer to go figure out what happened, what went wrong, and why did that. And the reason I came into the story is this particular guy was my father. And so for about a year, as he was dealing with it, he would come home from work, and I was a college student, and we talked about neural networks, which was the technology he was using of the day to try to solve it. And I developed a passion, and thereafter, it led ultimately to where we are today. And so I wanted to share that, in that I've had a long time as an engineer to think about how neural networks solve the problems that we're dealing with today. And so I want to talk about, since we're talking about how does deep learning affect digital transformation and what is digital transformation, I want to real quick cover that. It's common misconceptions there. It's not a channel, because people often think, oh, digital channel, that kind of thing. And it's not a project. It's not something you go off and stick a budget on and go do. It's the purpose of digital transformation is not to digitize an existing state, but to completely reimagine what kind of business model is appropriate to solve your problem. So if you were starting on your existing business today with the technologies that you have, and you were saying, how would we create this today from scratch? That's what it's about. So what we're really saying is that it's all about innovation. It's not about optimization, and that's a really common misconception. A lot of companies will go fund digital transformation projects, stick a budget, and they're trying to basically change something they already have in place with technologies. So the thing about it is digital transformation is itself going through a massive transformation right now. And that is because of AI. And as we talk about here, it's kind of led through this, in that we've had the cognitive revolution, which happened 70,000 years ago, agricultural revolution 12,000 years ago, followed by industrial, digital, and now the AI revolution. And they've gradually been changing society more and more. But now as we're getting into AI and it's impacting everything, we're talking massive changes to social, cultural, and economic interests all over the world, and it definitely affects digital transformation that all of our businesses are going to be going through. So digital transformation is at the very heart of this AI-driven change going forward. Artificial intelligence is already changing how these business models are being reimagined. So you could think of it as AI is the technology we're talking about, and digital transformation is that strategic process. And fundamentally, the technology is changing the fundamentals of how you apply the strategic process going forward. So I wanted to put this in a little bit of context. This lady is essentially the CTO at the United Nations. And she talks a lot about this in terms of how we should think about ourselves as technologists in this AI and digital transformation world going forward. And the ramifications, they're good and bad, that we all see in the news. And what do we need to do? What does our businesses need to do to transform ourselves going forward? If you look at the last 20 years, a lot of change has happened, but that's nothing like what we're going to see in the next 20 years, next 50 years, 100 years. We're going up an exponential curve with this. So you could think of that AI might be the last major innovation that humans are creating, because going forward, we're going to be using the AI itself to create those next innovations. And so you have a question there that we all have to answer as businesses of, the obvious labor things. We talk about jobs and things like that, but there's amazing great sides, amazing upside, and some downsides to contend with. So ultimately, the objective of digital transformation is going to be to try to figure out how to cope with the downsides while taking advantage of amazing upsides going forward. So this is the AI-enabled world of digital transformation going forward. So I've been throwing around AI a lot, and sometimes that can be hard to define. So can we define AI? Well, that's easier said than done, because if you ask 10 different AI experts to define AI, you're going to typically come up with 10 different answers. And so how do I know this? Well, because Adobe recently did this, and I was invited to be one of those AI experts that they polled. So we had a group in a think tank in New York City that was broadcast, and it was funny. You put all these people that are supposed to know all about AI, and the thing was, we were unable to define it. Every one of us had a completely different answer. So I say, I'm going to kind of share what my definition is, and it's perfectly fine to not agree with me on precisely, because there were at least 9 other AI experts in that room that didn't agree with me. And each one of them had the same dilemma. They all had 9 people that didn't agree with them. So I define AI in a very narrow context personally. I consider AI to be a marketing buzzword, and it evolves over time. It was the neural networks that my father was doing in the early 90s was AI. There were other things that were attached to the label, and as time goes on, different technologies get attached to that AI label. So it evolves. It'll probably be, my definition will evolve also. For 5, 10 years from now, it'll probably be a bit different. So these days, I take the fact that AI being a marketing buzzword, and obviously digital transformation is too, because that's evolving. And so I consider AI simply to be deep learning. There are other technologies you can argue are in there, and that's fine. But I think this is what's really driven this massive surge over the last few years. So I realize that not everybody will agree with my own definition. Princess Leia's looking pretty rough there, I think, with the stormtroopers behind her. But I did also want to share one other thing that's just an aside as we go on, and that is that we did all agree on exactly one key principle in that group of 10 people. We all agreed that you start with the customer, no matter what industry you're in, what your project is, where you're applying, and you work yourself backwards to the technology. So we couldn't agree on what AI was, but we could agree on what you do with it when you're trying to apply it. So what is deep learning? I want to talk about that for a moment. It's really modern AI that is working today. And it's an approach to machine learning that's driving the current artificial intelligence revolution. And it's an approach to machine learning that draws its inspiration from the human brain, statistics, and applied mathematics. So, and by the way, the quotes here are from the seminal textbook in the field, which is called the Deep Learning Textbook, just to note that there. And they note in the textbook, which is probably many of us understand here, that the things that are driving this at this point are the facts that we have new techniques every year. And right now, we have new techniques almost every few months. Giant data sets that are just getting bigger and more available, and obviously more powerful computers, whether they be cloud-based or NVIDIA supercomputers or whatever you want to have. And so what that really means is that you're talking about the modern application of neural networks to achieve the machine learning goals that you have. So you're learning from data without explicit programming. And that is neural computing. And this is a term you're going to see more and more in the years ahead. Because I was recently at the NVIDIA GTC conference back in, I guess it was February now, and I noticed that their CEO was talking a lot about neural computing, and it's kind of a shift in the way we're thinking about programming. Instead of being explicit, if this, then that, go through a loop, I have to think of everything as a programmer, we're now going to start having models that do a lot of that decision making, and we accommodate those models in day-to-day programming. This is a huge shift in computing going forward. So this is kind of how I see deep learning as AI fitting into the space. It is one type of machine learning. It's not the only type of machine learning. There are many other algorithms out there. Some of them, people will argue, also take part in that AI world. So obviously, I have the bias that I've already disclosed. And then those fit into the larger combined world of data science and computer science. So one of the things we tend to talk about deep learning a lot without, a lot of people don't really understand why. Why is it this? We keep talking about deep learning. It's so popular. You hear about it and everything. What is making deep learning such an amazing tool for us, or at least why are we talking about it so much? So I want to talk about what drives it. And this guy here is excited, I can tell you. And that is that you can precisely approximate any continuous function. So maybe not this crowd, because it's a fairly technical crowd, but a lot of people, they see that slide and they start to fall asleep and go, really? That's your big reveal right there? But it's a pretty powerful statement, because you're basically saying that nearly any imaginable process involves computing a function. And if you can approximate that function with neural networks, if that's possible, that means you can apply it to a lot of different problems. So this is huge. Neural networks are somewhat universal. And that means that deep learning is a universal approach to solving complex problems. So Homer's pretty happy about that, but deep learning is currently, as you're probably aware, right at the very peak of the hype cycle. It's magic. It can do anything. It can solve any problem in the world. I just said it was the universal toolbox, didn't I? But we'll talk a little bit in a few minutes about what it's good to solve and what things are maybe not so perfect for it. And having said that, I would recommend that keep in mind that it's at the peak of the hype cycle. Ignore the hype. Just ignore the hype on it completely and focus entirely on the practical applications. So let's talk a little bit about how this technology, how deep learning in the context of digital transformation is being applied out there in industry. So probably the first mainstream stuff was Google several years ago kicking off and talking about it. And that was kicked off by the idea that he noted that the last 10 years have been about mobile first. And we heard that so much. But the next 10 years, we're several years into that, is all about AI first. And so as they look forward, they have been, and we've probably experienced it. If you have Gmail and are doing Google searches and stuff, those services have been evolving very rapidly. And so you are seeing them go through all their services and implement AI, neural network models, wherever it makes sense to help them along. And that's an ongoing thing. And everybody else in the world has followed suit on that. It is becoming one of those things that everyone realizes they really need to do now. About a year and a half ago, close to, I guess actually it's been over that, it's been over 2 years ago now, this CIO was commenting that if you were looking back 3 years and you decided to get into deep learning then, you would have spent an enormous amount of money and effort and time with limited results. But if you were to wait 3 more years, you're going to be hopelessly behind. And I've had that slide for a while in various talks, and I found that as we're approaching that 3-year mark, I think he's dead on. I never knew if his timeline was right. I agreed with the sentiment, but I think his timeline is right because everyone's doing it now. Everybody is trying to figure out how to apply models. So if your company isn't, then you probably need to be thinking about that. Because in these years ahead, we're certainly going to consume and will probably be creating artificial intelligence at companies throughout the world and machine learning in the form of microservices. It'll just be normal programming, APIs that we're used to having. It won't be anything distinct and magical. So see, these are some of the more common use cases. And well, let me pop back. Just a second, I hit the wrong button there. These are some of the common use cases, and this doesn't even begin to cover all of them. This is a tiny smattering. Kind of by line, we're talking about kind of security, marketing, some of the different computer vision applications and speech recognition, obviously transportation, with us talking about automated vehicles everywhere, and healthcare is huge, and then financial. And as a matter of fact, these days, really everything in the securities market is regulated by these models. Some of these crashes that we've had recently where it drops hundreds of points in a few minutes and pops straight back up, all of that is computer driven by these types of models as they're learning to do it better and better. So Andrew Ngee in Harvard Business Review also put this out as just a basic way of talking about some of the use cases that you can apply these technologies to. And he did it in a very simple, like, I got a picture, are there human faces, and that's photo tagging. So you can take a look at that, and I'll make the slides available later on. But I really want to talk about what is today's AI good at. It's really good at solving complex but very, very specific problems. And oftentimes, it can do that far better than humans can. And that's where you're seeing giant strides in things that we see even on CNN about what certain systems are able to do so much better. You know, radiologists the last few years have been in a hard place because the CNNs of today, the convolutional neural networks, which we'll talk about, can analyze those images so much better than a human can, and that's being spread out. So what is AI bad at? It's really bad right now at problems that involve creativity or that change or evolve continuously. And that may not always be the case, but right now it is, ironically, it's a lot easier for a neural network to go and do the job of a radiologist, which is a highly specialized field, versus if you were back before the agricultural revolution and you were a hunter-gatherer, and there were so many different things that you needed to be able to do to survive on a day-to-day basis, neural networks would never be able to handle the complexity and diversity of all those today. So the real power equation going forward is humans plus AI. You have a bunch of different use cases. There's autonomous vehicles where you're essentially delegating that. Robotics, where it's a combination of collaboration and delegation. Interactions through either augmented reality, mobile, or conversational interfaces. I don't know about y'all, but I have both both Amazon and Google in my home listening to everything I say. In some cases, the same device. Both devices are in the same room. So that is the world going forward. So really, what AI is going to do in the near future is give us superpowers. You'll have the ability to work with that AI to do your job, but so much more productively than you ever could have done it before. So we talk about a world transformed. We're all familiar with Google's automated vehicles and the profound changes that's doing, that's creating in industry. It's moving from cars to flying vehicles to trucks on the highway. You name it, that entire industry is being digitally transformed through this technology. This is kind of a joke of mine that I found and I like, and it's that, are we going to just have bots? Everyone talks about bots. When I was at Accenture, we talked about bots all day long. I got to where I couldn't stand bots anymore because so many companies are creating bots for anything they want to do, which assists the people, their customers, their employees. And as we do that, going forward, it's going to affect all of our lives in a profound way in the fairly near future. Gartner has estimated that by 2025, half of our primary healthcare needs are going to be handled by bots. These technologies are already out there. They're getting much, much better very, very quickly. And so you're going to go to your iPhone or Android as your first mechanism for solving whatever your ailment of the day is. And you'll only go in and see a doctor once you get passed up. You'll no longer start with a primary care physician. You'll start with the bot and then work your way into that. And you'll get faster, better service as a result. So lots of bots. We're all building chat bots. Google's DeepMind is doing some amazing things in terms of cancer treatment. And you're also going to find that even in things like stopping violence, this is a system here that is able to, through microphones placed throughout a region, hear gunshots and route police much faster than they could have before based on neural networks analyzing where crime is occurring and giving the dispatchers an early go. So it's pretty amazing. So we've been kind of talking about use cases and how it affects the world. And I want to do a little bit of a deep dive for those of you who may not be familiar with exactly what, and I have this fellow again, apologize for that, and to kind of talk about how neural networks work fundamentally. So you're really talking about creating training that enables generalized predictions using known correct results. And this is called supervised learning, as opposed to unsupervised learning or reinforcement learning, all of which are in the space, but I'm kind of starting with the basics here. As you do that, you have to have, for training to work, you have to have a lot of known correct results. It can often be easily in the thousands, often in the hundreds of thousands or millions of samples that you can say, this is the reality. We have a historical record, And by using the historical record, we're going to be able to train a neural network to do this the way it should be done, based on that historical record. And so once trained, though, from that historical record, a neural network can give completely new things from existing, you can have a new input, and it can give you a completely new output based on that existing generalization, and it's likely going to be right. In a lot of cases, it's going to be 99+% right, which is incredibly powerful. So you're essentially talking about learning from experience here. And so this is a slide that kind of shows a toy neural network. You got a couple of different nodes, and basically you would start your training process by randomizing the weights. Each one of those nodes has a weight associated with it, and it has an algorithm that you put in called an activation function that does something with the numbers coming in. So you have all your data going in is in the form of a number. Those numbers get pushed through, processed by each neuron, and pushed through. They're fully connected from layer to layer. Every neuron at one layer goes to all the neurons at next. And you push that through, and then every neuron here accepts all the inputs coming into it, has the transfer function, and then activates that back out. And so you could almost think of this as trying to find the lowest error through the entire network to get to achieve your accuracy. And there are different ways of approaching that. So you get to the end, and if you're talking about using backpropagation, which is probably the kind of the granddaddy of the algorithms applied in the space, then it pushes those back using that known correct number, pushes them all the way back through and filters them to the beginning and makes adjustments to those weights, and then it pushes them back through again. It goes back and forth for every row of data you have in your set, which can be millions, as we discussed. And it's getting better and better and reducing that error down. And eventually, after what you're essentially doing is this search to find the right answer for that, you're going to get to a final neural network. And if you notice, the arrows represent the weights that are being applied. And you could then take this trained neural network, stick it out in the real world, take in new data for that same kind of problem that the network has never seen before, and it should give you a very, very good answer for that. And that's the fundamental way that feed-forward backpropagation works, which is kind of where everybody starts. And so you could think of this as a way of representing all these as a set of hierarchies. The layers are each taking what comes in before and creating a new node in that hierarchy. And so it's really a set of hierarchies that the neural network creates. They're each one conceptual at a different layer. So these are the common architectures that you're going to find. We just talked about feed-forward networks. There's also, for computer vision and for now other applications as well, convolutional neural networks are amazing. There's a new one that may replace them called capsule networks that a lot of us are focused on at this point. Recurrent is great for sequential problems that you're trying to solve. And generative adversarial allow you to generate new data by having neural networks essentially kind of fight it out. One creates things, and the other one has to discriminate whether or not it's real or not. And you work your way into new outputs through the two of those working against each other. I'm going to go pretty quick because we're short on time. Fundamentally, a convolutional neural network takes a big picture and breaks it down into what you could think of as features, and eventually it can feed that into that feed-forward network and identify what that is. Going beyond that is beyond the scope of our time, but fundamentally you need lots of data and you need lots of computation. So if you're going to invest in deep learning, you want to have all of these are kind of really startup concepts that you want to really do, because deep learning is definitely an area where you're not going to just do this and you automatically get results. You have to search your way into getting where you want to go. So startups or big companies that have a startup mentality within a team tend to do better than others on getting there. And there's a bunch of questions. Most of these are very typical data science questions that you probably have already used even if you weren't doing deep learning in terms of how you're going to get into this and what kind of things you need in place. I'll let you take a look at that as I move on. And this comes back. I mentioned earlier that we would come back to this. You have to start with the fundamental problem you're trying to solve and work your way into what is the right deep learning solution that you're trying to get to. So you want to analyze the problem statement. Can you solve the problem with simpler, less expensive tools? Because sometimes deep learning is not the right solution. There may be other machine learning solutions that are much quicker to get to without the investment. So deep learning can be expensive to scale. Once you get into large data sets and processing on those for complex problems, your training costs can quickly spiral in. I know somebody who accidentally spent $100,000 out of budget. I think he had a $10,000 budget for a small project, and he left something overnight and came back and he had spent 100 grand. So that was fairly painful. It really requires a strategic investment from your leadership team. And you really need to recruit the very best people you can find and train the people that you have so that you can get into this. That requires that you have a learning culture, and you need a mixture of different skills, not just data scientists. The teams that I've run have been very eclectic in terms of what their capabilities were. And that means you need someone who knows deep learning. Not all data scientists are familiar with it. So you need to make sure you have your data and have your data strategy in place. You need lots of data, lots of computation, as I noted, and then going through with the, sorry about that, I think I'm going. You need an executable AI strategy as a prerequisite. If you don't have your if you don't have your data strategy for your AI strategy, then you are going to feel a lot of pain. And if there's one thing that I've run into more often than anything else with other teams and with customers, is that they didn't figure out their data strategy ahead of time so their AI strategy would work. So that's where most organizations fail. So get that in order, have a process. It's really no different from any other data science process. Feature engineering, model selection, model training. Make sure that your software and systems are able to do what it is that you need them to do, and that you have a deployment strategy. And this is really where I want to finish, is that when we get to deployment, things get difficult. For me, when I was at both Accenture and Honeywell, we had a fairly standard environment that we were able to operate in. The usual cloud providers. At Honeywell, we also had our own hardware that we could use, and we had a bunch of great frameworks with which we could actually go. And we'd use TensorFlow, more recently PyTorch, and some of the others, and it really depended on who on the team wanted to do what, and we could get there. But, and that was pretty amazing that those frameworks were starting off with Docker and Kubernetes standard, the usual cloud technologies. But even though your open source tools are democratizing your accessibility to these technologies, when you got to deployment, that is where things got difficult. We would get to where we were deploying to one vendor's edge devices or another vendor's edge devices, and I don't want to call names out, but as we moved from vendor to vendor, we found that we had to completely relearn or re-engineer how we were approaching it. Sometimes we'd actually go back and have to move our models from one open source framework into another one because the vendor B supported it, vendor A supported that one, and so I think if there's one thing as we finish up that I have been hoping for the better part of the last year, maybe year and a half, it's that we would get better vendor support for being able to take advantage of the optimizations that everyone's hardware could do. The people are putting the acceleration in, they're supporting certain frameworks and not others, and so my vision as we close out of rainbows and unicorns is having a deployment environment that allows us to go through less pain, more of a common, unified way. So I wanted to finish this talk as I talk to this particular group and say, I hope that you will go out and those of us who are working in the space help us get there a little bit easier and a little bit better. And we may have some interesting conversations today about that. Having said that, I just want to say I welcome you to listen to my podcast. There it is. And if you have an interesting story, see me afterwards, and we'd love to get you on. And that's it. Thank you very much for listening.
We have time for a question if anyone would like to ask a question. Yes, gentleman over there.
I'm going to get some water as we talk.
Yeah. Go on.
What are the parameters in sizing up the number of nodes, sizing up the deep learning network?
So could you say that again?
Given a problem, how would you define how wide and deep your tree would be of those?
So when you go back to the process slides, and I know given the time, I will skip through them very, very quickly.
Sure, sure.
But when you're analyzing the problem, and realistically, you will come up with a candidate which is probably very much like somebody else before you has. We do a lot of transfer learning. And so you'll say, I have a problem, how have people solved that before? You go find a model where people have written about what they've done and you do that. And generally speaking, if you're lucky, it might work, but more often than not, it doesn't work quite as well as you want. So you keep iterating, and then you start saying, well, what makes my problem different from theirs? And you start saying, okay, I have these layers in this architecture that serve these purposes, so it's an engineering question is what it becomes. It's saying, as I separate the requirements this model that I'm transferring in to utilize did, and I have this problem over here, what makes it different? And then I start adding or subtracting parts to the architecture that allow me to get closer to that set of requirements. And then it's trial and error. You go back and back and back and try until you get there. Does that answer?
Yes, very helpful. Thank you.
All right, thank you very much, Chris.
Thank you so much.
So Chris is going to be around for the rest of the
I will.
day.
Yep.
So, and try not to stand on his foot, which I nearly did earlier. Okay,
Thank you very much.
Right, it is my very great privilege and honour to introduce an old chum of mine, James Davies, who has more titles than I have. He's a fellow, he's a VP, and he's general manager of the machine learning group in ARM. So, Jem's going to come and talk to us about, well, guess what? Stuff, yes. Do come over here, old chap. I think this is still the same one. Is this the button we need? Yeah, that works. Right.
Technology?
Right.
Good man. Nursey will be along later to help you out. So good morning, everybody. My name's Jem Davies, as Dave Rustling says. A long, long time ago in a galaxy far, far away, he persuaded me to join a company called ARM, where I was a Linux kernel hacker. And the stories that are told of those times, tragically, are mostly true. More years have passed now than either of us cares to admit, and now I'm an ARM fellow, and recently I took over as general manager of the ARM's machine learning group. What am I doing here today apart from reminiscing with an old buddy and drinking too much in the bar? I'm here to talk to you about steps we're taking to enable developers to use machine learning across the widest variety of ARM-based platforms to enable us to take advantage of this great technology that Chris was talking about. It all went past so quickly, I think I agreed with several of the things he said, but I'll have to think about it later to see. I think he set me up rather nicely for this talk. How will we do this? Well, we're going to do this by driving the definitions of open standards in this area and collaborating with you, the best in the industry in open source. Damn, it works. What's happening? Machine learning changing incredibly fast, as Chris was talking about. It's a field of really, many, many moving parts. But we believe the time is right when key areas and applications and use cases are starting to stabilize, and the time is now right for collaboration. I want to thank George for his keynote on Monday, and in that you'll have seen that Linaro announced a new machine learning intelligence initiative that ARM is going to be part of, and I'll talk a bit about what part of means. This initiative, Google announced their endorsement of this with a statement, and I quote, "The TensorFlow team is excited to expand support for edge devices, and we're looking forward to integrating with the ARM-NN library." Right, well, there's a clue. What are we doing? We're getting involved. We're collaborating with all of the companies to define these open standards to support this machine learning to be rolled out across a wide variety of platforms. In addition, we're donating a huge body of code to bootstrap this initiative, and I'm going to talk about that body of code in this talk. Although we were already open source under an MIT license, we're donating ARM-NN to the Linaro Machine Learning Initiative. ARM-NN is an inference engine designed for efficient inference running at the edge on the sort of devices we all work on. And following really quite significant pull from a number of companies working in this space and developers who wanted to get involved and contribute to this project, we decided that Linaro is the best place for that collaboration to happen. So we're donating it to the initiative, remains under an MIT license, very permissive license, and we encourage contributions from everybody. The governance will be organized by Linaro. We think this is the right thing to do. We will continue to work on it. There will be massive contributions from us continuing. We are moving all of our development into the open. So if you don't want to see how sausages get made, I suggest you stay well away. So I think by now, particularly after the previous presentation, nobody would doubt the effect that ML is having and will continue to have on all of the things we're working on. Notwithstanding the absolute massive hype, and Chris, you may have noticed that Gartner put machine learning at the absolute peak of inflated expectations. I paid good money for Gartner to come in and present the Gartner hype cycle to us, and then they put machine learning at the peak of inflated expectations. So imagine my disappointment. But actually, if you're right, ignore all the hype. If you get through it, we will see that ML is enabling key new use cases and also massively improving existing ones. And in something that is perhaps surprising to some of us, if not all, we're seeing this actually across the full spectrum of devices, right from very basic Cortex-M microcontrollers through Cortex-A, through GPUs, and also dedicated neural network processors. It's probably easier to try to list the segments that aren't using machine learning. An experiment that I was recommended, and I recommend it to you, is think of any classical method of processing algorithms, whatever, and just type that in and add machine learning, and then put that into Google. And you'll find a whole range of research papers coming out where people have tried the most bizarre topics and replaced them with a machine learning implementation. My personal favorite is intercontinental ballistic missiles. It's actually a very difficult control plane problem, and very few countries have actually ever got it right. Controlling rockets by lighting a very, very big fire at one end and then moving the other end a bit, it turns out to be remarkably hard to do. All you need to do is write a model of that system, crash about 4 trillion rockets, and then you can have a machine learning process run that for you. It's just extraordinary the things you can apply this to quite successfully and get better results for many values of the word better. Cheaper, faster, more optimized, you name it, you get it. I've listed a few on this slide. I don't think really I need to go through them. I think you all know them. Autonomous driving is only ever really going to take off successfully once, in technological terms, there are many litigation and liability issues to sort, but in technological terms, once the ML advances become mainstream, both in classical sort of object detection and segmentation, but also the cognition that goes into it. Face identification really only got critically reliable once we applied ML techniques. Speech recognition's gone from isolated keyword recognition through to being able to analyze continuous streams of speech using a very small percentage of the CPU budget on sort of mobile devices. Huge improvements in existing capabilities. And image processing, I think, is going to be a huge thing in the consumer field. It's actually, if you think about it, it's an ideal target. Because what do we want? We want things to look good. Can we actually define good in algorithms that say, oh, take this pixel, sharpen that, bring down the gamma, do this, do that? No, we can't. Actually, it's completely heuristic method. So it's ideal for putting vast quantities of images up, getting people to vote on whether they like them or not, and having those images processed in a way that makes us feel, oh, that's nice. Oh, I'll buy that one, not that one. A neat side effect is something that I was working on before in the image processing field, which is actually different groups of people have different ideas about what good looks like. There's a body of work being done to look at genetic disposition towards perceiving color and image in different ways, for example. This just falls out. You just go, I'll have that version, please. I could go on. We could be here all week with me talking about applications that are possibly slightly less exciting, like logistics and distribution and things like this. But one thing I bring out from all of these things is that all of these are decisions where the data is available at the edge. If training is a problem which is solved where you have large quantities of example data, high quality annotated data, then inference is something that you want to do near the test data. And generally speaking, that is at the edge on battery-powered devices, which, curiously enough, is something we care about a lot. Technology. So, if we look at machine learning and look at the challenges associated with it, and Chris talked about some of this in his talk, we have problems in different domains. Okay, that's slightly scary. Please don't do that again. You could be an ML domain expert, you know, a data scientist or somebody working in ML frameworks, a researcher. You could be a problem domain expert. You could be a doctor, you know, a logistics planner. You could be a computational linguist. Or you could be a platform expert. And at the moment, you've got the situation where some sort of domain experts are providing their knowledge and expertise to the ML researchers and to allow some experts to interpret the data. But this sort of knowledge and expertise transfer between these different domains is not working well, and it is holding us back. Linaro is obviously the meeting ground for the third pillar, the third domain expertise, which are the platform experts. We are the ones who need to get our heads round Chris's final problem, which is enabling ML across the wide variety of ARM-based platforms. And obviously, ARM is committed to working on this part of the problem, and in fact have been working on it for the last few years. Most of the use cases I talked about there, and I think, yeah, that is actually legible, they run on CPUs and GPUs today. But we're going to need to transition some of those to working on other types of processors and accelerators. And those accelerators are not going to be a one-size-fits-all problem. We're going to need different accelerators to solve different computational problems in different markets. So naturally, you know, as a software engineer, or at least was once a software engineer, you know, I reach into my toolkit of things to deal with this, and I come up with a software abstraction. We've got lots of machine learning being run on ARM platforms today. We've got lots of new use cases coming along. We've got some people running perfectly happily on CPUs and GPUs today. We've got some people who are never going to need a neural network accelerator, and we've got some people that do. And we know that we can't rely on the cloud in this situation because it's inappropriate for a bunch of reasons I'll talk about next. But you're going to want to run more efficiently on future devices. You're going to want to run workloads between different parts of the device. You're going to want to run workloads between different devices. And we need to move workloads between the different accelerators. There's a whole heap of choice here that non-experts in this field are currently failing with. We need to make that easy for them if we are to get the benefit of bringing ML techniques to the sort of devices that we build. And standard software inference engines is going to be part of that problem. I talked about running software at the edge and why I thought the cloud wasn't the right answer for everything. It's instructive perhaps to look at a little bit of history here. Most of the ML research has been done by people who had a hyperscale data center out the back. So the obvious tool to use to solve their ML problems was the hyperscale data center. But actually, there are very solid reasons why that isn't going to work for all examples. Clearly going to work for some, it's clearly working for some today. But in the future, there are three primary reasons why there are pressures to move that to processing at the edge. Laws of physics, laws of economics, actually the bits of economics I believe in, and the laws of the land in several jurisdictions. So if we look at the laws of physics, first of all, bandwidth, there is not enough bandwidth in the world. We're talking about upwards of billions, possibly a trillion. My new boss, Massa, who runs SoftBank, talks meaningfully about a trillion connected IoT devices. I can't count that far, but it's going to be a big number. Many of them are going to have high-resolution video cameras attached to them. Connecting 500 billion devices and sending a continuous video stream up to a data center in Seattle, having it processed there or in some data center of your choice, submerged under the sea off Iceland, whatever, and then send it all back again. It's just not going to work. The internet will break. There is not that much bandwidth in the world. Power. Increasingly, of course, as we get into modern devices, it's more power expensive to transmit the data than it is to compute it locally. And that's before we start looking at the power consumption of these huge data centers. You know, the power problem, for us, you know, we have some power problems we understand about batteries and things like that. They have similar power problems. Believe it or not, it's actually almost impossible to get more than 10 kilowatts into a rack full of computers and then take the 10 kilowatts of heat out. It's almost impossible to get more than a megawatt into a shipping container and get it out again. You know, they have serious power problems. And then, of course, you have to buy that much power. Stop me later and I'll tell you about the bloke who wanted to run the Human Genome Project and got told to build a power station. So, yeah, the power is significant. Latency, we're accustomed to talking about latency as a user experience problem. You know, we all hate it when the thing doesn't seem to respond to us. You've watched me struggling here. But actually, latency gets to a point where it's rather more than simply tedious. You can imagine a car doing visual recognition of things in front of it. The speed with which it recognizes a speed sign or a stop sign or a child walking out in front of it is actually singularly important to the process involved. And you just imagine what that says when you go, ooh, sorry, I need to retransmit that. The 3G signal's a bit weak. Yes, 4G makes that better. Yes, 5G makes that better. But it's never going to make this problem go away. There are certain classes of computation we're simply going to have to do locally at the edge. Moving on to cost then. I can do no better than quote Google, who said, if everybody in the world uses Android voice assistant for 3 minutes every day, we will have to double the number of servers we own. So this is not we're not finessing a bill of materials cost here. These are simply eye-watering sums of money that we cannot ignore. It's cheaper to provide a certain number of compute cycles in a small battery-powered device than it is to provide those compute cycles in a 5 nines reliability data center. It just is. And we can also get into questions about who pays that cost, but that's a sort of an interesting aside. Reliability, well, I talked about the interruption to your mobile internet service. There are certain things that just simply have to work. We have to guarantee their performance, we have to guarantee their reliability, their latency, and so the only way to do that in some cases is to take ownership of that problem ourselves. I'm not having a go at the cloud. The cloud is brilliant, but we need to be thinking about using appropriate tools in appropriate places. And then finally, the law of the land, having been through the laws of economics, let's go back to the law of the land. Security and privacy are, of course, concepts that are becoming incredibly important to us. And as we get into the Internet of Connected Devices, then there are significant concerns expressed in that place. We're connecting very personal data. If you think about the phone in your pocket, its accelerometers can already work out with about 90% accuracy what gender you are. It certainly knows when you're sitting down, when you're walking about. It can easily work out when you're asleep. It knows where you are. It knows whether you're in your house, somebody else's house, somebody's house you shouldn't be in. You know, I could go on. There's very personal data here. We are going to want to protect this carefully, and part of the story of protecting that data carefully is not sending it to other people unless you absolutely have to. So I think I've set out, you know, pretty clearly why I think there are fundamental principles. This isn't just me saying this is a good idea. This is observing there are fundamental things, laws of nature out there that are going to push as much as possible of this processing to the edge. And what is that processing? Well, at ARM, we see machine learning as simply, and yes, I deliberately put sneer quotes around that, simply a software problem. ML is for us just a compute workload. It's, of course, an increasingly common workload, and it's a slightly different type of compute workload to some we've seen before, and that has effects on our processor design. But at a high level, we just need this workload run as efficiently as possible, as optimized as much as possible across the widest variety of our platforms. The guy at the top of this stack doesn't care what's in the hardware underneath this. He just wants it to run reliably, easily, and for him not to have to spend all night getting it to work. He likes to go home on time. That was a non-gender specific use of the word he, obviously. So we need a software platform that will support this, and we need to plug into the existing ML frameworks that are already out there. We've been working on parts of this solution for some years now, and last year we announced Project Trillium. We don't have all the parts. We don't intend to have all of the parts. We intend to take the best of the parts from other people and build this, this platform together. But by now we've got the best part of 100 engineers working on the frameworks that are set out in this rather beautiful architecture diagram. We have our inference engine, ARM-NN, which sits on top of our compute library, which consists of code optimized to run on the wide variety of processors that you find today on your platforms. And of course, for different partners, we find different platforms. From Cortex-M, which is actually being used much, much more than we expected for processing for keyword spotting, audio phrases, etc., through Cortex-A and Mali GPUs being used for higher performance applications. On mobile today, you've got the applications from people like Google and Facebook that are already using ML on mobile, on CPU and GPU today. And finally, of course, we're going to need to support these new dedicated neural network processors, and not just the ones produced by my group at ARM. We need to be realistic about this. This is an open field. Lots of people are going to come in and innovate in this space, and we need to allow, and more than allow, we need to encourage that. The performance and efficiency of these new neural network processors is so high that they're not only accelerating the top right, where people want absolute massive performance, but it's also making possible new applications by dint of that efficiency and that capability. My favorite is things like full frame rate, full resolution scene identification being used to drive picture quality improvements in set-top boxes. You know, this is not a mobile application. This is guys going, oh yeah, well, we used to sort of work out what was in the picture, and then we lovingly hand polished all these pixels to make it look good. Now we're just throwing away the front end. We'll just we'll put it all through a neural network, we'll identify what's in the scene, and then we'll polish it according to our secret sauce. So with Project Trillium, we've started, we've got this ball rolling, but we need your help to do the next part. Talk a little about experts, as indeed Chris was talking about. It kind of looks as though ML is simple. You just throw everything at a neural network and it, out the solution pops. Everyone knows what part of an image a cat is, or indeed a hot dog. Even a one-year-old child can recognize a cat. Well, it turns out there's actually some interesting wrinkles there. A one-year-old child shown a picture of a Manx cat, which is a cat genetically having no tail. The one-year-old child says that's a cat, but it's got no tail. It's confused, but it knows it's a cat. You show it to most deep learning network systems, and they go, no idea what that is. Models have hidden problems. For example, it turns out, if you're not careful, snow was being used to identify pictures of wolves. You thought it was identifying a wolf. Actually, it was fixating on the snow. You just didn't notice that until you brought a husky along, and the husky gets identified as a wolf because the husky's rolling around in the snow as well. There was another one where tanks were being identified by the bright conditions when the photograph was being taken. It wasn't actually identifying the object itself. Speech recognition works well because we've now got a combination of classical approaches, things like extracting the features via FFT, working in the frequency domain, taking out the phoneme extraction, and then working on sentence probabilities and things like that. Well, actually, if we rework that and take the phoneme and the sentence probabilities together, throw it into a machine learning model, we get a huge improvement in accuracy of speech identification. That work's been achieved because you've got researchers from one field standing on the shoulders of a huge body of research already being done in other fields. Experts are very much still needed in this space. We are a long way from making this idiot-proof. Worse than that, we've got to provide an environment in which the experts can work with each other, because we are going to need the experts to combine their expertise. So there's a lot of talk about ML being the Wild West, and in some ways it actually is. But we've got a lot to work from, albeit several places where there's unnecessary separation, duplication, and some religious wars. Clearly, no field of human endeavour in computer science would be complete without some good religious wars going on, and we've certainly got some of those. We've reached a natural position where several companies have produced systems that understand their data and produce useful results out of their data and understanding their problems. But it's now getting to the stage where we want to consolidate shared interests and try and address some of this fragmentation and duplication. We don't need so many intermediate forms. Indeed, I'd argue some of the intermediate forms aren't really intermediate forms at all. Just F-writing your internal data format out to a file does not make it a standard. You know, there are several out there that are not thought through formats that we can use for multiple tools and frameworks and inference engines to use. We need to embrace other people's work here. We need open standards, open data representations. We need to be able to work on that in an environment where people can collaborate in an environment like Linaro. We need to share the inference code bases. We've already got good results with ARM and Google sharing Android NN using some of our optimized code and scheduling code. We're seeing good convergence on Android with tools and frameworks. Android NN, absolutely the standard in this space. But the same's not yet true of other variants of Linux. We're seeing far more fragmentation. We're seeing those inference engines often exploiting ARM compute library for performance, but we need to consolidate on a single inference interface. There's really no need for multiple places in this space. With that in mind, we might be able to tame some of the worst of the Wild West. I talked about the three pillars of the problem earlier, the domain experts, the ML experts, and the platform experts, and how we need to bring these pillars together to make this possible. The prize at the end of this would be to allow experts in one of the areas not to have to be experts in all three. Because if we don't fix that, this simply isn't going to work. Nobody, or very, very few people, can become experts in all three of these problem spaces. I'm sure it is obvious to all of you that Linaro is the place where we should be able to work together, ARM and yourselves, to help solve the platform part of that problem and make those platforms useful and available to other developers. And this isn't, although I've talked about a lot of the usual suspects of ARM, Linaro, Google, and Facebook, this isn't just them. This is huge. The ecosystem for this is pretty much everybody you might care about. There are experts in data services who understand how to interpret and understand that data. There are experts in algorithms being used to solve the common problems, packaged up for others to use in a way where they don't have to understand them so deeply. There's companies building software services around this. There are companies and developers building tools to debug and optimize our code. And of course, there's lots of companies working on the many platforms and IP components of those platforms being designed across all the variety of end market segments. And all of these people need to be able to speak common languages and be able to talk to each other. I hope I've made clear that all this requires us to come together and collaborate as developers. We want you to join the work so that we've got the best minds working on this. ARM-NN and the compute library, as I said, were already available under the MIT license, but we got many requests to get to it closer and to be able to contribute, and that's why we're opening up the code and getting it governed, open source governance as well as open source license, in order for people to contribute. We think it's really important that we get this right. It's taken us over 100 man-years of effort already to work on ARM-NN, the compute library, all the work we've done on performance analysis, methodology, and benchmarking. And ARM has been and will continue to be committed to development on ARM-NN, but now we'll do it in the open with you and all of your contributions. We hope to leverage the best of Linaro's forte for combined development, which is key because we need your methodologies for continuous integration and testing to make progress in this fast-moving space. And we need Linaro's approach of collaborative development, making this the place where the smart people want to work. But let me be clear, of course, ARM is in no way backing off this now. This is just the start. I'll talk a little here about what's so important about ARM-NN. What did we get for those 100 man-years of effort? Well, one of the design choices from the start was not to produce our own high-level framework. There are enough of those already. Personally, I would argue way too many. Keep going. The industry won't continue to support 20 of these frameworks. They simply won't. It's also instructive to observe if you look at effort as measured by open source commits, you can see that one or two are absolutely streets ahead of the others. But ARM-NN is not taking sides in this. ARM-NN was designed from the start to plug into the existing frameworks. We're not taking sides in this war. In subsegments such as mobile, there are existing inference engines, and of course we can connect to those, work efficiently with those. There's simply no point in reinventing the wheel for Android. But for embedded Linux systems, we need to start setting some hardware standards and taming some of this Wild West. And finally, we have highly efficient backends already optimized for some of our CPUs and GPUs. We spent tens of man-years of effort just on that alone, and we want the world to take advantage of that. I said we're committed to allowing other third-party IP into this. We've got 3 serious companies working with us already, looking to integrate their accelerators into our framework, and we are committing to helping that, making that possible. And it's also worth noting ARM-NN is already proven in production. We have already more than one deployment shipping in high-volume production devices. Drawing to a close then, please make the most of this day. There's a full day session on this in this room following the keynotes, and I highly recommend you make full use of this, as well as grabbing people in the breaks, talking to them, including myself. In Rob's talk, he's going to give an overview of the ARM-NN design and code base. He'll talk about the interfaces, why they exist, and what they are. He'll talk about how people are using it today, and also give a peek at the future of some features that ARM are going to be contributing to the code base in future. After that, we've got Pete Warden and Mark Charlebois from Google and Qualcomm, and I'm sure those are going to be great as well. And these are just the morning sessions. We go on in the afternoon with talks from AWS, NXP, Xilinx, and others. Talk to each other. Let's work out between us, because between us is the answer to this problem, how to speed development on machine learning on more use cases across the widest variety of ARM-based platforms. Thank you very much.
Thank you very much. We won't do questions. So as